Today we want to look at parametric equations. We're going to use parametric equations when we want to describe a curve in two-dimensional space where one coordinate is not a function of the other coordinate. And I'm going to start with the classic example from the Greatest Hits album, a circle centered at the origin. So recall that a circle of radius 3 will have an equation x squared plus y squared equals 9. Now, we can't write y as a function of x, and we also can't write x as a function of y. When we try to solve for one of these variables, we have to take a square root, and square roots lead to plus and minus. So in particular, if x squared plus y squared is equal to 9, then I can write y is plus or minus the square root of 9 minus x squared. The plus square root of 9 minus x squared will correspond to the top half of the circle, and the minus square root of 9 minus x squared will correspond to the bottom half of the circle. So we can't write y as a function of x because each x has two outputs, a positive and a negative, or each x corresponds to two different y's, a positive and one negative. We can't do this in the other direction either, where x, we could solve for x, but we have the same issue. X is plus or minus the square root of 9 minus y squared. When x is positive square root of 9 minus y squared, we're dealing with the right half of the circle. And when x is minus the square root of 9 minus y squared, we're dealing with the left half of the circle. So as a function, we only get half of the circle. So I can't write one coordinate as a function of the other coordinate. A lot of times when we talk about looking at a graph, when we want to talk about a function, we talk about a function passing the vertical line test. If a vertical line does not hit the graph more than once, then y is a function of x. Usually when this is introduced, we just say not a function, but specifically referring to y is not a function of x. Note that we can write x as a function of y, in which case we'll be concerned with the horizontal line test. So when x is the positive square root of 9 minus y squared, x is a function of y. So each input y corresponds to just one output x. But we can't get the entire circle without two functions if one coordinate has to be a function of the other coordinate. That's the issue that we have. So what we do for another way to get around this problem, rather than just using two functions when we could use one, is not force one coordinate to be a function of the other coordinate. We'll define the coordinates independently as functions of some parameter. So what we want to do in parametric equations, with parametric equations, we define the x and y coordinates separately as each as a function of some parameter. So we're defining the x and y coordinates independently of each other and both as functions of some parameter. We define the x and y coordinates independently of each other and instead define them as functions of some parameter. usually t. So we'll write the coordinates of the curve will be two functions. So the coordinates of the curve will be a function x of t and y of t. And then we'll have to define t for some values of t. So we'll say here's a function of x, here's a function x of t, here's a function y of t. Plug in these t values. So these are the t values that we want to plug in. We got to tell our reader what values of t we want to plug in. So for t between a and b, so we plug in all the values from a to b and generate a bunch of points. And here the x and y don't have to be functions of each other. They're functions of some parameter. And so we don't have to worry about things like vertical line tests or horizontal line tests or any of that stuff. So getting back to our classic example, we could define x of t to be 3 times the cosine of t and y of t to be 3 times the sine of t. And then we have to say for, let's say, t between 0 and 2 pi. Here we'll get the parametric equations of that same circle that we had before. The other thing that we're doing when we're defining a curve with parametric equations, since there's a lowest value of t and a highest value of t that we're plugging in, we're also giving a direction to our curve. So if we just think about plugging in values of t, when t is equal to 0, x of 0 is 3 times the cosine of 0, so that's 3. Y of 0 is 3 times the sine of 0, which is 0. So we start at the point, well, I know what it's going to be, so I'm just going to draw it. So when t is equal to 0, the curve is at the point 3, 0. So here's the point 3, 0. When t is equal to, let's say, pi over 4, cosine and sine of pi over 4 are both root 2 over 2. So I get 3 root 2 over 2 for both. So not only are we going to get this whole circle by plugging in all these values of t between 0 and 2 pi, we are also assigning a direction. So note that the curve also has direction. When t is pi over 2, we get the cosine of pi over 2, which is 0, and sine of pi over 2, which is 1, times 3 is 3. So we'll be at the point 0, 3 when t is equal to pi over 2. And we can keep plugging in values all the way around. And we say to stop at 2 pi. So when t is equal to 2 pi, we're back to the beginning. Cosine of 2 pi is 1, times 3 is 3. Sine of 2 pi is 0 times 3 is still 0. When t equals 0, so we at the point 3 0, when t equals 0, and also when t equals 2 pi. So by taking t from 0 to 2 pi, we go around the circle one time counterclockwise. So this raises the question, can my calculator do this? And the answer is probably yes, otherwise I wouldn't have raised the question. But we have to tell that if we're going to do this on, say, our TI-84, we have to tell the calculator that we want to do parametric equations. The default when we hit y equals is to write a function. Specifically, y is a function of x. Because all your calculator is going to do here is take a look at your window range and plug in all the x values and plot them. So that's why it likes this simple format. So if we want to enter parametric equations, then we have to tell the calculator that we want that. And that goes into the mode. And then we'll have to drop down to parametric and highlight that. Now, when we hit the y equals button, rather than getting y equals, we get parametric equations. I've got x1 and y1. So earlier, apparently I did 2 instead of 3, so I'll change these to 3s. So here we've entered x of t and we've entered y of t. We've got to tell the calculator what values of t to plug in, and that'll take place in the window. So the window, it says t min and t max. I want to start off t at 0, and I want to end t at 2 pi. So there it is. The t step is how often we're going to plug in. So when I first started drawing this out, I did 0 and then pi over 4, then pi over 2. I did steps of pi over 4. Since I'm using a calculator and it can plug things in quickly, I'm going to use a step of 0.1. So I'm going to plug in 0, then 0.1, then 0.2, 0.3, and so forth. Or I'm not going to do it. My calculator is going to do it. So I'll hit graph. And so not only do we get the circle that we expected, we saw it build in the direction that we wanted it to build. It went once around, counterclockwise. Once we have this basic shape, we can pick out, by controlling the parameter, we can pick out specific values of, or specific parts of the circle by controlling the parameters that we plug in. So if I take my window and instead of going from 0 to pi, I go from 2 pi, I go from 0 to pi. This is only going to give us the top half of the circle. Go from 0 to pi. Won't go all the way around the circle. If I want to just say the upper left corner, the quadrant 2, I could change my start to pi over 2. And then we'll only get that quarter circle. So by controlling the values of t that we plug in, so I could get, say 2 pi over 3 and go to 5 pi over 3. I can pick out which portion of the curve that we want. Questions?
Yeah, Professor Lich.
Uh-huh.
On the very top, we have the example, xt equal 3 cosine t, y t equals 3 sine t, between 0 to 2 pi. Could you explain again, please? The t equals 0, pi over 4, pi over 2, and then 2 pi. Where
I'm just picking values of t to plug into x of t and y of t. So all we're doing is choosing values of t.
Oh, then you plug for the x and the y. Okay.
Yep.
For example, if we plug the t for 0, xt we get 3. If we plug t for pi over 4, then the xt will be 3 square root 2 divided by 2. Am I correct?
Correct.
What is the one on the right again? What are those meanings?
What is what one on the right?
The one on the right, you have like very bottom, 3 comma 0 when t equals 0 equal to pi.
So this point, this right here says that when t is equal to 0, x of t, so this says when t is equal to 0, x of 0 is 3, and y of 0 is 0.
Correct.
And 3, 0, these are the coordinates, 3, 0.
Oh, okay.
So those are the coordinates, and that happens when t is equal to 0.
You don't mind if you go back to the previous page, Professor Lich, on the previous page that you have.
Yeah.
You don't mind? If you don't mind. Yeah.
What's your question?
The previous page, there was 4 of them. What were those the function or not the function?
So these 4 half circles,
Yes.
those are if we have x squared plus y squared is equal to 9, we can solve for either one of those variables, but we don't get a function. We can't describe the entire circle with one function. Because when we solve for y, we get plus or minus the square root of 9 minus x squared.
For example, the one on the top left, example y equal plus square root 9 minus x squared. Is that the top half? So this is not the function, am I correct?
So that is a function, but it's not giving us the whole circle. If we look at x squared plus y squared equals 9, in that equation, we can't write y as a function of x, and we can't write x as a function of y.
Okay, thanks for now.
Because we get the plus and minus. The plus corresponds to the top half of the circle, the minus corresponds to the bottom half of the circle.
Okay, thanks, Professor Lich. I will review that again. Thank you.
So in this example, with x equals cosine and y equals sine, we can describe this circle. And by controlling the parameter, we can control what portion of the circle. Notice that no matter what values of t I picked, the circle always goes in this counterclockwise direction. If we change some things up, if we look at another example, let's define x and y. Let's switch the roles of x of t and y of t. So let's say x of t is equal to 3 times the sine of t, and y of t is 3 times the cosine of t. And we still want to go t between 0 and 2 pi. Let's take a look at what happens if we graph this. And we'll use our calculating machine to do it. So I'm going to change my window back to the default 0 to 2 pi. Those are the values of t that we're going to plug in. And I'm going to change my functions. In this case, I want x to be 3 times the sine of t and y to be 3 times the cosine of t. Let's see what graph we produce here. So notice in this case, we produced the same circle. The curve is the same, but it started at a different point and went in the opposite direction. So we're still getting a circle, but in this case, we started off at 0, 3 when t equals 0, and it went clockwise. So the curve was the same, but it had a different start, and it went in a different direction. Let's say the same circle. It's a different curve. Different starting points and different direction. There's only 2 choices, left and right, so I guess it went the opposite direction. Now, if we change the values of t that we plug in, we'll still get different starting and ending points. So if we go from 0 to pi, instead of the top half of the circle moving counterclockwise that we had in the previous example, here we will get the right half of the circle moving clockwise. Zero to 2 pi gives us the full circle. This makes sense because if we think about the equation of that circle, if we think of the equation of the circle, x squared plus y squared is equal to 9. If I plug in 3 sine of t and 3 cosine of t into this equation, I get 3 sine of t squared plus 3 cosine of t squared equals 9. So I get 9 sine squared t plus 9 cosine squared t. I can factor out the 9, and sine squared plus cosine squared is equal to 1. So it makes sense that these parametric equations will produce the same equation, the same graph as x squared plus y squared is equal to 9. They are compatible. Any questions?
Yes, Professor, where is that sine, the very bottom? We have 9 sine squared t plus cosine squared t equal 9. Where that's cosine and sine? What happened to those?
Sine squared plus cosine squared equals 1.
Oh, that's the identity, isn't it?
That's an identity.
I see the difference. You mentioned something. This one is like go to the clockwise because it seems like we switched the x and the y from the previous problem, right?
Yes. We also changed where it started.
So would we have the x and the y? If the y go first, then would it be counterclockwise? Is that what you mean?
No, it's just for this one. It's because we have a circle in this case.
Okay, thanks.
The point that I wanted to make was that since x and y are defined independently of each other, and we're plugging in a bunch of the values of t from some interval, that gives the curve a direction to it. Where we had counterclockwise in the previous curve, we have clockwise in this curve. So when we define functions, when we define curves with parametric equations, we assign a direction to the curve, a starting point and an ending point, and a direction in between. Any other questions? Oops. So another type of parametric equation that we should be familiar with, very popular, especially here in calculus, where we talk about tangent lines all the time. We want to have understand the parametric equations of lines. So when we describe a line, we need to describe a point to start and a direction to go. And usually we describe the direction with rise over run, called the slope of the line. But here, the x and the y are acting independently. So if we look at these, if we start coming up with, let's plug in some values of t. If we start when t is equal to 0, we get x naught and y naught. Oops, spelled not wrong. When t is equal to 1, then we add a to x naught one time. And we add b to y naught one time. When t is equal to 2, we'll have added a twice. And we'll also have added b twice. And then this could go on. Once again, we're just choosing values of t and plugging them into x of t and y of t. If we put this on a graph, so I'm going to start here at x naught, y naught. When this is when t is equal to 0. When t is equal to 1, we will have added a to the x and b to the y. So this point will be at x naught plus a and y naught plus b. Where I've added a down here. I say every one unit, I usually use this one. So we add b to the y's, and we add a to the x's. And then if we do that again for t is equal to 2, we've just added a twice. And we added b to the y twice. So here we are adding a And here we are adding b. And our coordinates at this point will be x naught plus 2a, y naught plus 2b. And this is when t is equal to 2. Note that the slope of this line is rise over run. In this case, will be b over a. I knew there was a reason I wanted to change these from a and b from the book, but so when we define the slope, we define the slope to be the rise over the run. And in this case, b is the rise and a is the run. Now, we know that we can write, when we're writing a line, we can write y as a function of x, we can write x as a function of y. That's why we think so, and we do this a lot because that's why we think of rise over run all the time. Because we can define slope of the slope will be constant, so we can always just take the rise and divide it by the run and figure out the direction of the line. But we also want to make sure that our new thing, parametric equations, fits with our equations of lines. Now, notice that we can have, by controlling the values of t that we plug in, we can just plot line segments. If I just plot this from t equals 0 to t equals 2, I would just have this one segment of a line. If I want to get the entire line, I'd have to plug in all values of t. Also note that a is how x is changing with respect to t. So in terms of calculus, a is the change in x with respect to t. So a is a change in x with respect to t. B is how y is changing with respect to t. So b is the change in y with respect to t. Also, if we just take the derivatives with respect to t, derivative of x naught is 0 because x naught is constant. The derivative of at with respect to t is just a. If we take these values and put them into the slope where b is the rise and a is the run, I would have dy dt over dx dt and if I do dy dt divided by dx dt, the over dt parts cancel out and I just get dy over dx. So we've just looked at circles and lines, and these are curves that we understand pretty well. We know what their equations look like. We know what they look like in terms of functions and how limiting having one variable be one coordinate be a function of the other coordinate is. What we want to be able to do in general is describe a curve that can't be written as a function at all. So for example, if I say, let's say this curve we're defining a path. All we have is a path in R2. But there's no way I could write x, the coordinates here, x as a function of y, or y as a function of x. If I draw a vertical line test, I see that y is not a function of x, because here's a place where one x corresponds to 3 different y's. And if I try the horizontal line test, I cannot write x as a function of y, because here is a horizontal line that hits the function twice. So I can't write x as a function of y. I can't write y as a function of x. But if x and y are defined independently of each other, I can describe this curve with parametric equations. So at any point on this curve, I have an x of t and a y of t. And if we think about what's happening with the x's go up to this point, and then down to this lowest point, and then back up to b. So the x's are going to go up, down, and then up again. And the y's are starting here. They go down, up, down, up, down, up. So down, up, kind of flat, and then up at the end a little bit. We can describe the x and y coordinates independently of each other and relative to some parameter t. That frees us up to draw any kind of curve in space. This is especially important when we start drawing curves in spaces, higher dimensional spaces. Because if I have a x, y, and z coordinates, if I try to write one coordinate as a function of the other coordinates, I don't get a one-dimensional curve. I get a two-dimensional surface. So we still are going to want to describe one-dimensional curves in higher dimension spaces. And so parametric equations is going to be our way to do it. We want to free ourselves from having to write one coordinate as a function of the other coordinates. That is very limiting. It's useful when we're learning, but we tend to dig a hole that we have to dig out of now. Any questions?
Yeah, for first solution, this one we call parametric equation of line.
Mm-hmm.
And then I see the note you write down m equal rise over run, b over a. This is not the slope, isn't it? No, right?
Rise over run is the slope.
So this equation.
The slope is rise over run. When we want to write y equals mx plus b, that's a different b. The slope is rise over run.
But this one is b over a, isn't it? Correct? No.
For in this case, yeah. It's when I say y equals mx plus b, it's not the same b. So when I say y equals mx plus b, it's not that b.
Okay.
This is why formulas are awful. Because we start using these names for these constants, and we detach ourselves from the meaning of what those constants are. It's really handy for things like Pythagorean theorem. We can just say a squared plus b squared is equals c squared, but that is not the Pythagorean theorem. That's just a squared plus b squared equals c squared. The understanding that has to go along with that is knowing that c squared, the c is the hypotenuse and a and b are the other two legs. If I label one of the legs as c, then all of a sudden it's not a squared plus b squared equals c squared. If the hypotenuse is b, then it's a squared plus c squared equals b squared. So this is why formulas in general are kind of trash as far as when we're learning things. Formulas are for when we've already got the stuff down and we just need a handy way to remember it. But formulas get in the way of understanding when we assign too much meaning to just the letters that are involved. All right, so I've put up new assignments from the rest of chapter 4. So those will be due on Sunday as usual. That's going to do it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.